Okay, so for chapter 36, we're going to do problem 1. Let's see, and also problem 13, 43, and then 68 and 74. All right, so let's start with the first one. So the first one says the distance between the first and the fifth minima of a single slit diffraction pattern is 0.35 millimeters with a screen 40 centimeters away from the slit. When light wavelength 550 nanometer is used, find the slit width, and also which you want to find A, and calculate the angle of the first diffraction minimum. So this would be the diagram that I would draw. So you have this is where the slit is, and this is my central axis, and this is where the screen is. And this distance, that's called a capital D, which is 40 centimeters. Okay, and it says the first and the fifth minimum. So let's say this is my m equal to 1, and the fifth, let's say this is my m equal to 5. Okay, and let's say location is y1, location here is y5. So just based on this, it says the separation is 0.35 millimeters. So I will write down y5 minus y1, that's equal to 0.35 millimeters. Okay, and then we know that this is the diffraction pattern. Then we will use a sine theta. So we know that a sine theta 1 is equal to m lambda. M is 1, so it's 1 lambda. And then a sine theta 5 is 5 wavelength. Okay, and then so you can actually just subtract a minus a sine theta 1 from a sine theta 5. So we will have a and then sine theta 5 minus sine theta 1 on the left hand side, and on the right hand side you will have 5 lambda minus lambda, so that's 4 lambda. Okay, so then a is not known, lambda is given. Sine theta 5 and sine theta 1, how do we get those information? So if we know that the y1 here would be the y1 here would be there's a angle theta 1 here, and this is angle theta 5 there. So what we can do is that because this being so far away, your sine theta can be roughly equal to tangent theta when the angle is so small. Okay, so in other words, this becomes tangent theta 5 minus tangent theta 1, and that's equal to 4 lambda. So tangent theta 5. So what is tangent theta 5? This is y5, and this is d. So you have the a, and then you have the y5 over d, and then minus y1 over d, and that's equal to 4 lambda. So your a, not knowing what a is, but your y5 minus y1 is this, and your d is this, and your wavelength is this. So when you plug in those numbers into this equation, just make sure that everything is in SI unit, in meters, then you should be able to calculate your A value, which is, let me see, which is 2.51 times 10 to the negative third in meters. Okay, so that is the slip width. This is basically how you approach this problem. And then once you have the that problem, then you also find what is the angle theta 1. So we would plug into this equation. We know that a sine theta 1 is equal to lambda. So your a, you plug into this equation, and your lambda is this number, and make sure that you convert it to meters. Then you should be able to calculate your sine theta 1. And then so sine theta 1 would be, let me see what number I got. Sine theta 1 is 2.19 times 10 to the negative fourth, meaning that after you take the inverse of sine, then your theta 1, you should get a numerical value that is 0.01255 degrees. Okay, so this is basically how you do this problem. Okay, all right. So that is problem 1, and the next one I want to do. The next one I want to do is problem 13. So let's look at problem 13. So we have a monochromatic light with wavelength that's 538 nanometers. It's incident on the slit with width that is 0.025 millimeters. So that slit width is A. The symbol is A. The distance from the slit to the screen is 3.5 m. We use capital D for that. Consider a point on the screen that's 1.1 centimeters from the central maximum. You want to calculate the theta at that point. You want to calculate, what is this? You want to calculate alpha, okay? And you also want to calculate the ratio intensity to that point, at that point to the intensity at the central maximum. So this is how I will draw the diagram. So let's say again, this is where the slit is, and this is my screen, and this is my central axis, and then this is my D, and then let's say this is your y1, and this is your theta 1. Okay, and so the y1 here is 1.1 centimeters, and the D is 3.5 meters, and then wavelength is this, and your A is this. Okay, so you want to calculate theta. So what you can do is a direct, you can we don't know. Sorry, it's not y1. It's just y, because it didn't say which order. Let's see, calculate theta at that point. Okay, so we don't know whether this is the first order or second order, things like that. So we should just saying that we have a point here that is 1.1 centimeters above the central axis. Based on that information, how do we calculate theta 1? And since we know this distance, we know the D, so tangent you can either do, so let's do tangent theta 1. So you have I'm sorry, not theta 1, but theta. So again, let me just erase that. So tangent theta is equal to y1, is equal to y over d. Okay, so your y is 1.1 centimeters and your d is 3.5 meters. So after you plug in the number, make sure that they have the same units, then you should be able to get tangent theta that's equal to 3.14 times 10 to the negative third. And then once you have that, then they can infer the angle. So the angle is equal to 0.18 degrees. Okay, so that is part A. And then you want to calculate alpha. So if you remember, when we went over diffraction, alpha is defined as, so the formula for alpha is this. So alpha is equal to pi A lambda, and then times sine theta. Okay, so we have everything in front of us. We have the pi, and our A is this, and our lambda is this, and sine theta is, you have the theta here, so you can plug in that to calculate your sine theta. So after you plug in the numbers, you should be able to get a numerical value that is equal to 0.458 radians. Or if you want to express that in degrees, then you can just multiply this by 180 degrees divided by pi. Then it is going to give you 26.26 degrees. Either way will work, but you just have to specify whether that's in radians or in degrees. Okay. And then you want to calculate the ratio. Part C says you want to calculate the ratio of intensity at that point to the intensity at the central maximum. So the equations for intensity for diffraction pattern is this. So we have the I log theta. So intensity is the function of angle, and that's equal to the intensity at the maximum, which we use I sub m, and then we have the sine alpha over alpha, and then you square it. So I want to caution you that, you have the alpha here, which should be, you should use 0.458 in radians. And then when you use the this expression sine alpha, really depends on the setting on your calculator, whether whether you set it to be in degree mode or in radians. You want to make sure that when you punch a number, you're conscious about your setting. So that's why, when I calculate the 0.458 radians, I also calculate the degrees, because most of the time your calculator will be set in the degree mode. So so when you plug in this number, so you want to calculate ratio. So you would have the, let me just write it here. So I log theta is equal to Im. That's your ratio, and that's equal to sine. So I will write down sine of 26.26 over alpha. Alpha, I will put down 0.458, and then I will square it. Okay, so your final answer. So the ratio, let me write down here. So the answer will be 0.933. Okay, so that's the answer for this part. So the calculation is straightforward, as long as you have the alpha. The thing is, you just want to make sure that this one, the one in the denominator has to be in radians, and the top one, sine alpha, if your calculator is set to be taking the degrees, then you have to use a degree. Don't use a radians, otherwise your numbers will be off. Okay. So this basically how you approach this problem. And then the next one I want to do is problem 43. Okay, so problem 43 ask how many bright fringes appear between the first diffraction envelope minimum to either side of the central maximum in the double slit pattern if the wavelength is 550 nanometers and the slit separation is 0.15 millimeters. And here it should be A. A is 30 micrometers. A here is the slit width. So you want to find out. You want to find out how many bright fringes within the first big envelope, and what is the ratio of intensity of the third bright fringe to the intensity of the central fringe. Okay, so diagram will look like this. So let's say this is my angle here, and this is the intensity. And the first envelope, let's say it produce the diffraction pattern like this. Okay, so this is when m is equal to 1. This is for diffraction pattern, the big envelope. This is where the dark fringe, occur. Within that dark fringe, between this dark fringe, then there's a, this is the envelope, and inside you would expect bright fringe. You would expect, bright fringe to occur because of interference. So the question is, how many bright fringes are bound by this, first diffraction minimum, like this. So we know that this is when the m equal to 1 for the first order for the dark fringes. This will have a corresponding theta here, right? So our question is, first of all, we need to figure out what is the angular extent that the bright fringe will be confined within this this range. So the first thing is that if we do A sine theta, because this is the diffraction pattern. So let's use A sine theta. Okay. So we can even put down theta 1 because this is the first order. A sine theta 1, that's equal to m lambda, and your m is 1 because the first minimum, so 1 lambda. So you can calculate sine theta 1. So that your sine theta 1 is equal to lambda over A. Okay. You can either so after if you've done this kind of problem enough, that you will know that you don't really need to calculate theta 1, because all you need is actually just sine theta 1. Okay. So you have the lambda is this value, and your A is this value. Okay, so you can plug in the number if you want to do that, and then you can get your sine theta 1 that's equal to 0.0183. But we don't really need that value, as you can see later. Okay, so now we figure out our sine theta 1 is this, and then so this will have a corresponding theta 1 here, theta 1 there, meaning that the bright fringe within this big envelope has to be confined within in this range. Okay, so then how do we find the bright fringes inside this big envelope? So we have to know that these bright fringes are produced because of the double slit interference pattern. So then we have to use the equation for double slit interference pattern. So for the bright fringes, if you recall, the bright fringe is d sine theta. That will be d sine theta that's equal to m lambda. Now, I don't want you to get confused with the m like this. So I'm going to use the dummy variable. I'm going to use m prime instead, okay, for the bright fringe. So you have the d sine theta that's equal to m prime and then lambda. Okay, lambda, the wavelength does not change. The d is the slit, d is the slit, separation. So sine theta, and then m prime lambda. As you can see, your m prime can start from 0 to the values that it would allow. So we need to see what is our m1, and you can see that your sine theta. So for each bright fringe, there's an angle. For each bright fringe, there's an angle. So whatever angle that you have here, it has to be less than theta 1, right? Because theta 1 is the boundary. So based on that information, how do we calculate? Our m prime? So we know that our m prime is equal to d sine theta over lambda. And we also know that this sine theta has to be less than this sine theta 1. So in other words, this is equal to this, and this thing has to be less than sine theta 1. So in that case, what we have here is that we would have the so this will be like d sine theta 1 over lambda. Okay, m prime is equal to this, and sine theta has to be less than sine theta 1. So you have the d so it's less than d sine theta 1 and then over lambda. So your m prime has to be less than d over lambda, and then we plug in sine theta 1, which has this expression, lambda over a. So lambda get canceled. So this means that your m prime, the number of orders, the bright fringes within the big envelope, has to be less than d over a. Okay, so what is d over a? Your d is 0.15 millimeters, and your a is 30 micrometers. So when you do the d over a, you will get a value that is 5. Okay, meaning that your m prime has to be less than 5. Okay, so your m prime, the order of the bright fringe will start from 0, which is here, and then the next order is plus or minus, because it's symmetrical about this. 1, 2, 3, and then 4. And we don't have 5 because it has to be less than 5. So altogether, Altogether, there are 9 bright fringes, okay, because 0 plus or minus 1 all the way to plus or minus 4, so that's 9 fringes that will be allowed within this big envelope. Okay, so that's your part A. That's how you do this kind of problem. The rationale is that calculate the angle that is from the dark fringe from the utilize a sine theta that's equal to m lambda, and then knowing that your m prime has to be is this, and that has to be less than this bound, and then from there you can figure out what the m prime is. Okay, so that's part A. And then for part B, it says what is the ratio of intensity of the third bright fringe to intensity of the central. So in other words, if this is your m prime, if your m prime is equal to 3, what is the intensity ratio of that? Okay, so to do that, let me erase this. So now for part B, because you want to find out the intensity ratio of the third bright fringe, we don't even need this anymore, because this is just the extreme, and we're now doing the one that's actually the third bright fringe. So the equation to do for the double slit is this. So I3, intensity at angle I3 is equal to the central maximum, and then times the cosine square, that's beta, and then sine alpha over alpha, and then square. Okay, and then our beta is equal to, so when I do this, we'll start with the beta, and our beta is pi d lambda, and then sine angle, and because we're dealing with the third bright fringe, so I would say sine theta 3. Okay, and so what is our sine theta 3? You can see that we have pi d and lambda, but we don't have the sine theta 3. So if you remember, d sine theta 3 is actually equal to m prime lambda. So your m prime here is 3. So then your sine theta 3 is actually 3 lambda over d. So I'm going to do this. So I have my pi d over lambda, and then replace what we just said. That'll be 3 lambda over d. So you can see that lambda cancel, d cancel. So your beta is actually 3 pi. Okay. So once you have that, then we are able to calculate alpha then. Once we get our beta, and then let's do our alpha. So what is alpha? Alpha is defined as pi a over lambda, and then sine, same angle. We're dealing with the third bright fringe here inside this envelope, so it's sine 3. And we will calculate our sine, from this expression. So we have the pi a over lambda, and then this will be the 3 lambda over d. So you can see that lambda get canceled. So you have here is that you have the 3 pi a and then over d. And a has this value, d has this value. So when you plug in the number, you'll get your alpha, which has the value of 0.6 pi. Okay, so again, I'm going to express the alpha in radians and also in degrees, so that when we do the calculation, it will be easier. So then after you convert it to degrees, that will give you 108 degrees. Okay, so we have our pi. We have our beta, and we have our alpha. Then we are ready to calculate. We're ready to calculate the ratio. So for ratio, let me use a different color so I don't have to erase anything. So so the ratio will be the I theta 3 over Im, and that's equal to cosine beta squared. Beta is 3 pi, and then times sine of the angle alpha, which is 108, and then over the 0.6 radian, and then I'm going to square it. Okay, so cosine 3 pi will give you, and then square it will give you 1, and then sine, you can punch to a calculator, sine of 108, and then divided by 0.6 pi, and then you square it. So your final answer after you punch to the calculator, you will get that the third bright fringe, this intensity is about 0.254 of the maximum value. Okay, so the ratio is 0.254. So that's basically how you would approach this problem. As you can see, when we do part B, I'm not using the angle from part A because part A is reversed to this angle. For part B, we're talking about this angle, the third bright fringe. So that's a little bit different. And to find out that angle, you will use d sine theta, that's equal to m lambda, and then see what your m is, then that will determine what that angle is. Okay, alrighty. Okay, so next one I want to do. The next one I want to do is problem 68. So if first order reflection occurs in the crystal at Bragg's angle 3.4 degrees, and what Bragg angle does second order reflection occur from the same family of reflecting planes? So this is the Bragg's the Bragg's law, and the applications of Bragg's law would just be when you have wave incident on the crystal, then it's going to have so the crystal itself is acting as a grating. It's going to produce the diffraction pattern. And the equation that we use should be this. That'll be 2d sine theta. So instead of a d sine theta, it's actually 2d sine theta. That's equal to m lambda. Okay. And so here it says that the first order occurs at 3.4. Okay. So what about the second order? So what we can do is that 2d, based on the info, we're not given the d, so let's just say we have 2d and then sine of the first angle theta 1, and that's equal to the first order. So m is equal to 1, so that's your lambda. And then you have the 2d for the second order. I will have this sine theta 2, and then that'll be 2 lambda. Okay, so you can do the ratio here. So the dd to get canceled. So you don't really need to know the spacing of the planes, and then a lambda cancel. We don't have to know the wavelength, and the theta 1 is 3.4. So you can actually plug into this and then rearrange that. Then you'll be able to get your theta 2. You'll be able to get your theta 2 that has a numerical value of 6.81 degrees. Okay, so that's just a very straightforward application of the Bragg's law. Okay, and then the last one I want to do is problem 74. So this also is applications of diffraction that utilize the Rayleigh's criterion. So an astronaut in a space shuttle claims she can just barely resolve 2-point sources on Earth's surface, 160 kilometers below. Calculate their angular and linear separation, assuming ideal conditions. So lambda is 540 nanometers, and the pupil diameter of the astronaut's eye to be 5 millimeters. So the situation will look like this. So this is a blown up version. So this is the Earth, and this is the astronaut, and her and then she can barely resolve 2-point object that because so blown up version. Let's say like this. Okay, so this is true object on Earth. So this is the linear separation, and this this is the angular separation. Okay, and so and then the distance from where she is to where the object is 160 kilometers. Okay, so I want to find out what is the angular separation, and we know that in order for the astronaut to barely resolve 2 objects that's 160 kilometers away, certain criteria, the radius criteria has to be satisfied, and radius criteria is that your theta, the angular separation theta, has to be equal to theta r in order for it to be barely resolved. And how do we calculate our theta r? Our theta r is has the expression of 1.22, and then wavelength, and then times the diameter of the lens, which is the pupil of the astronaut. So so we can plug in the number. So lambda is this, and then the diameter is this. So when you plug in to this equation, make sure that the units are consistent. Change that to meters. So you should be able to calculate a numerical value that is 1.3176 times 10 to the negative 4th radians. Okay, so that's your theta. So your theta has this value. All right, and then once you have your theta, so this is the angular extent of that, of the the 2 points separation. So what is the linear separation? If we know the angle, we can actually just calculate the arc length. So the linear distance, so I'm going to call that L, will just be this value multiplied by this value. Okay. And so when you do that, then you'll get that is 21.08 meters. So this is a simple demonstration of how, when you have an object, when you have two objects that can be barely resolved, the criteria that has to be, the criterion that has to be satisfied is Rayleigh's criterion, which is 1.22 times lambda over the diameter of the lens. Okay.